So these are intermolecular forces, the strongest of which is ion-ion. So that might be something like sodium chloride. It's an ionic bond. The sodium has a +1 charge, the chloride has a -1 charge, hence why I call it chloride instead of chlorine. And it's an ion-ion bond. It's the strongest of these forces I am listing. The next strongest, the second strongest, is the hydrogen bonding phenomenon. Hydrogen bonds are it's probably easier to draw it out, but they will always involve fluorine, nitrogen, or oxygen, and a hydrogen that's bonded to one of those, engaging in a fluorine, an oxygen, or nitrogen's lone pair electrons, and creating sort of a bridge that's not what we would consider to be a covalent bond, but it fools a lot of people in that way, and certainly fools a lot of electrons in that way. Dipole-dipole interactions involve permanent dipoles in a molecule, so you've figured out this molecule has an actual dipole moment, that one side of the molecule has a plus charge and the other side of the molecule has a minus charge. And they have an overall dipole, but it's not temporary. I mean, this is a permanent thing. You would expect there to be a higher likelihood of an electron being on the negative end of that dipole than the positive end. And you'd expect that all the time. So it's a permanent dipole attracted to a permanent dipole. So that's not as strong as hydrogen bonding, but it's still stronger than the weakest one, which is London dispersion forces. And unfortunately, this phenomenon has a lot of different names. So I'll try to go through a bunch of them right now, and you're going to hate me because it's just, something with so many names. It's kind of like P. Diddy, right? he's sometimes he's Sean Combs. If he was paying me, he'd be Mr. Combs or Sir. And if he to some people, he's Puff Daddy, and sometimes he's P. Diddy. So many different names, right? Or Snoop Dogg for that matter, right? Like he has like an actual name, and then his parents call him, or his mom calls him Snoop, and now he's what's he call himself? Snoop Lion. Thank you. Yeah. So many different names. So here are some different names for London dispersion forces. They are sometimes called London forces. They're sometimes called van der Waals forces. They're sometimes called dispersion forces. And probably the best name, because it's actually descriptive, but very few people use it, is induced dipole forces. And these are forces between molecules that have a temporary dipole and like another molecule that has a temporary dipole. So two particles or two non-covalently connected things that have a temporary dipole, each of them, they kind of align anti-parallel and are attracted to each other based on that induced dipole attraction. So let's draw some of these out. So this is ethane, and I'm just drawing a molecule that really doesn't have a lot of interesting features because everything has induced dipole. So I'm trying to find something that has just induced dipole, intermolecular forces to demonstrate. Remember, it's intermolecular forces, so I need to show it kind of being between two molecules, or that's conceptually what they're about. Inter meaning between different ones, not inside of the molecule. So each of these bonds is pretty nonpolar. I mean, the electronegativity difference between carbon and hydrogen is fairly small, so they're not going to really be polar bonds. Moreover, there's some symmetry to this molecule. I'm not really drawing it in 3D here, but there is symmetry to this molecule. So even if each of these was a very polar bond, it wouldn't be polar overall because they kind of cancel each other out in terms of direction, and the overall dipole vector would be basically 0. What can happen here is, even though there's not really much of a permanent dipole, electrons that are being shared in a bond could temporarily be more located around a hydrogen. They could be found over here a little bit more, or on over closer to the hydrogen than they are to the carbon, and that would create a temporary dipole, a temporary partial charge difference. So you might end up having electrons being a little bit closer to the hydrogen here. So it would create a temporary delta minus, and it would create like a temporary delta plus here. And I mean, you could have this happening throughout the entire molecule to where it actually is like a negative charge here and a positive charge over there a little bit. So that temporary dipole interaction could actually line up anti-parallel to an opposite interaction. You could have, or an opposite induced dipole. So you could have here the electrons being a little bit less on the hydrogen here temporarily, and a little bit more here at the carbon for this bond, again temporarily. So these are not permanent dipoles. I don't want you to think this is happening and it's forever changed. They're temporary, but whoops, it's kind of cool. This bond ends up having a temporary dipole where there's this delta minus or partial negative charge and this delta plus, and it can line up anti-parallel to the dipole that's there. So this negative charge would be attracted more to this positive charge because it's closer to it. Then this positive charge would be attracted to this negative charge. Said that wrong. So these two are closer together, they're opposite charges, than these that are the same charge and are repelled from each other. They're a little bit further away in space. And these two are the same. They're also further away than these two are. So by lining up anti-parallel, you end up getting something of a overall attractive force. Just like if I had two magnets that had charges like this, right? If I had a negative charge on this end of the magnet and on this pole I had a positive charge, I could get them to actually attract each other if I just line them up like this. They would actually sandwich together and just clunk down each other, and you'd expect them to do this, right? Like you'd expect them to just like gravitate, or I guess be attracted and jump right at each other and press against each other because of that force. They have the overall same charge. They both have a charge of 0, but because this pole is actually closer to its opposite charge than it is to its same charge, and this pole is closer to its opposite charge than its same charge, they actually can have an attractive force if they're oriented in the right way. And you can have this happen in molecules as well with induced dipole interactions. I suppose this could also just happen end to end as well. You could have a molecule that has like one end be slightly negative and the other end slightly positive, and then the slightly positive end of another induced dipole could come up to that slightly negative end, just like you could have two magnets that are lined up like that. And there would be, so whoops, no! I gotta like flip it around. Hang on, gotta change the poles so I can illustrate that for you. So, minus, plus, like this. Just pretend I didn't do that last thing. Like this, right? Amazing. I'm so good at PowerPoint and Paint. So there you go. That would be a positive or a favorable interaction, and the force between these two magnets would press against each other. You could have a similar thing with dipole-dipole interactions and induced dipole interactions. The only difference between dipole-dipole and induced dipole is that they are temporary in induced dipole interactions. So these van der Waals forces are actually temporary. This is not a permanent dipole, and you would expect this to be fleeting, and ultimately it's not that powerful of an interaction, at least like per interaction. So if I had a huge chain, like a huge polyethylene molecule that was like this with just lots and lots of carbon hydrogens, a chain that goes on like hundreds of times, these interactions would actually start to add up a lot. So if you have a very, very long molecule, you might have some of these weaker interactions start to become as powerful as stronger interactions because there's just so many more of them. Okay, so that's induced dipole. For dipole-dipole interactions, you need to have a permanent dipole. So let's go ahead and work with a molecule that has one, and I'll show you how to build up from first principles a molecule that has a dipole. All right, so let's consider ammonia. So here's ammonia. If you were to look at the periodic table, nitrogen has 5 valence electrons, and each hydrogen has 1 valence electron. So that means that the 3 of them together have 3 valence electrons. I'm just multiplying. And that means in total, this molecule has 8 valence electrons. Now, if I wanted to fill every duet and octet that the atoms that comprise this molecule want to satisfy or can satisfy, I would end up having 8 electrons to fill the octet of nitrogen, and 3 times 2, because each hydrogen wants 2 electrons in its duet, 6, so 3 times 2 is 6 electrons to satisfy the hydrogen duets. That would be 14 electrons overall. So I would expect that there's going to have to be, since there's like this difference of 6 electrons between what are wanted to be had surrounding each of the atoms and what's available in terms of valence electrons, I would expect that there would be a difference of 6 electrons that are going to be met by bonding, or could be met by bonding. So 6 bonding electrons, 14 minus 8 is 6. And I would expect, so 6 bonding electrons. How many electrons are in each bond? 2, right? So that means that I'm going to have 6 divided by 2. That's 3 bonds. And I might also expect that since I have 6 bonding electrons and I have 8 valence electrons total, how many non-bonding valence electrons will I have? Of the 8 that we are budgeted, how many have we not used up? 2, right? 8 minus 6 is 2, so we have 2 non-bonding, non-B electrons. Okay, bonding electrons. Those are abbreviations. It's not actually like BE, like the word B. Okay, so let's go ahead and try to draw out a Lewis structure based on this. So here's nitrogen. It's got 5 valence electrons. And then here's hydrogen. Whoops. That's not bad hydrogen. I'm going to copy it. And each hydrogen has how many valence electrons? 1, right. So I'm just drawing 1 hydrogen electron around every hydrogen. Okay. So now I'm just going to form some bonds because I know that the duets of every hydrogen are not satisfied. So we're going to form bonds until we've satisfied each of those. And also the nitrogen does not have a satisfied octet because it has 1, 2, 3, 4, 5 electrons surrounding it. So I'm going to go ahead and replace pairs of electrons with bonds until I start satisfying things. So whoops. Here's 1 bond. I'm going to, at this point we have 2, 4, 5, 6 electrons around nitrogen, so I can do more bonding. I got rid of 4 electrons, so I need to draw 2 bonds to account for those 4 electrons. So there's another bond, and there's another bond. All right, let's make sure everything makes sense here. Nitrogen has 2, 4, 6 bonding electrons and 2 non-bonding electrons surrounding it. So that's 8 valence electrons surrounding nitrogen. Its octet is satisfied. Each of these hydrogens has 2 bonding electrons around it. So that means each of the hydrogens' duet rules is satisfied. Okay, let's make sure we didn't invent anything or create electrons where there weren't any valence electrons. There are 8 electrons total in this picture. 1, 2, 3 bonds, so that's 6 electrons in bonds, and then 2 non-bonding electrons, so that's 8 electrons total. That's the number of valence electrons we started with, so that's good. That's a good check to make sure I didn't do anything crazy. And our predictions for the number of bonds and the number of non-bonding electrons are accurate here as well, so that's a great sign. So this is the Lewis structure for ammonia. Now we have to figure out what the geometry of ammonia is and whether or not there are dipole moments. So if all the bonds here don't have any dipole moments, then this thing would be a nonpolar molecule. However, if you were to look at the periodic table, you would find that nitrogen is way to the right of hydrogen. And if you were to look up the electronegativity of nitrogen, you would find that it's way more electronegative than hydrogen. That means that each of these bonds has a dipole. And now I'm drawing stuff over the Lewis structure. This isn't what you draw in the Lewis structure, but this is how I draw the dipole moments of all these bonds. I'm drawing the dipole moments towards the more electronegative element because the more electronegative element has a partial negative charge because it hogs electrons, and each of the hydrogens is more electropositive, less electronegative element. It has a partial positive charge, each one does, and I signify the partial by putting a delta, and I signify the positive by putting a plus. And then when I draw these dipole moments, I do so by drawing an arrow towards the partial negative charge, and I put the tail end at the partial positive charge. Okay. This is not a 3D structure. Now I have to figure out what the geometry of this is to figure out whether or not these dipoles cancel each other out or whether or not they sum up to an overall dipole moment for the entire molecule. This nitrogen in the Lewis structure was surrounded by electrons that were in 4 separate places. Bonding to this hydrogen, bonding to this hydrogen, bonding to this hydrogen. That's 3 separate places. And then a lone pair of electrons. So just as an aside, even if this is a multiple bond, I would only count it as one place. So every bonding to another element, that's just one place. Could be a double bond, triple bond, whatever. It's always going to be counted as one place. So here I have bonding to 4 different elements. That's 3 different elements. So that's one place each, or 3 places. And I also have this orbital being occupied by electrons on nitrogen, so that's another place, so 4 places total. The parent geometry for having electrons in 4 places around the central atom is tetrahedral, but not all 4 of the sites are occupied by bonding to elements. One of the sites is vacant, or is filled with electrons, so this is going to be trigonal pyramidal. It's going to look like this. And the hash marks indicate that the hydrogen is receding into the plane or into the whiteboard or into the chalkboard or piece of paper you're drawing on. And the wedge, the hydrogen is coming out at you a little bit. And here the hydrogen, just like with a line as a bond, is in the plane of the paper. So if I had to say which one's furthest away, it would be this hydrogen with the dashes, then this one, then the most closest to you is actually this one that's popping out at you. I suppose eventually we'll have courses that have 3D glasses, and then this won't really be an issue. We'll have special stuff to do this. But until that day, you're stuck with this. And those are those electrons I'm trying to draw in. They look horrible, but just go with it. So here are my horrible drawings of electrons. And the bond angle between each of these hydrogens, you would expect before you kind of approximate that or include the idea that the electrons, the lone pair electrons, actually take up more of the sphere around the nitrogen. You'd expect that these things would be, from a tetrahedral perspective, they would be 109.5, I think, degrees. And it's going to be a little bit less than that because these electrons will take up more of the coordination sphere around the nitrogen. So this will be 107.4, I believe, if memory serves. It's a little less than 109. So this is how it looks. It looks like a tripod, and there's no camera on it because the electrons are filling the space that would have a camera on the top of the tripod. But these are all legs of the tripod. And if you were to draw in the dipole moments on top of these bonds, it's pretty clear that if I was to... Ooh, that's going to look ugly. Oh well. Deal with it. If I was to average out all of these dipole moments, the overall dipole moment would just be one that points up. So for the entire molecule, there's a positive end at the hydrogens and a negative end at the nitrogens. This has a partial negative, and these have partial positives. So at the feet of the tripod is a partial positive charge, and at the place where the camera would be placed, there is a partial negative charge. So this molecule overall has a dipole moment. That means that ammonia molecules can actually participate in dipole-dipole interactions. So they don't just do induced dipole interactions. They also do the much stronger dipole-dipole interactions, permanent dipoles lining up so that there's attractive forces between different charges. Okay, so let me show you what this looks like. You would have, actually, Come on, Joe. Aha! Alright, the miracle of paint, once again, saving you a little bit of time. So we have this nitrogen, right? And this ammonia molecule, and I need to rotate this thing 180 degrees. The nitrogen, hey! Everything still works. There's rotational symmetry in all the letters. That's wonderful. Right, gang? I didn't have to redraw anything. Yay for me. I got to do this one more often. So, this has a partial negative charge on this side, right? Partial positive charge on this side. And this has a partial negative charge, partial positive charge on the hydrogens over here. Partial negative charge, excellent, delta minus. So they can align anti-parallel with each other and actually have a interactive force based on this dipole moments. They actually attract each other just based on electrostatic interaction, based on charge interaction. And you could actually have these, if I can select them correctly, you can actually have them lined up like, actually now it would be good if I didn't flip them. Oh well. Actually, watch this everybody. Ba-da-da. Nice. Oh, what am I doing? Even better. Watch. Learning curve is not too good for me. Alright, there we go. So you have them line up like this, and you would actually also have a attractive interaction. Because the positive end of this nitrogen, this ammonia molecule, would actually line up with the negative end of the nitrogen. You could actually have them getting close to each other that way. There'd be an attractive force. Okay, so that's dipole-dipole, and that's, you know how to do this. Because now you know how to make Lewis structures, you know how to create the geometries, and also assign dipole moments. All of those skills are culminating in this one thing you can do very well. So I could give you a molecule and ask you if it has a dipole moment. You'd be able to tell me. You'd be able to tell me if it's going to have dipole-dipole interactions. You'd even be able to tell me, just based on this interaction alone, that this has more attractive force between molecules of ammonia than molecules of argon, atoms of argon, for example. So argon's a noble gas, doesn't have any bonding. So guess what? I mean, argon doesn't really have any of these permanent dipole interactions. It's just a sphere of electrons. So, or, you know, not exactly a sphere. It's like a sphere with like p orbitals that kind of approximate a sphere if you add them all together a little bit. But, you know, it's pretty close to being, one side is not a lot different than another. And you'd have like another argon atom, and as gases, they're surrounded by like electron clouds, right? So you have like electron clouds. You can depict them as like spheres of like 90-degree probability. So you could conceivably have some electrons that are on this side more than on this side. So you could have a temporary dipole, an induced dipole, and then you could have like a partial negative charge here temporarily and a partial positive charge here temporarily. And conceivably, you could have a partial positive charge here and a partial negative charge there. And all this is possible, but this is not as strong of a force as a permanent dipole always being there, always being a potential source of attractive, a potential source of attractive force. I'm really close to a song already. Just gotta like work out a couple more rhymes and I'm ready to go. So you could already predict, just based on what we've done so far today, that argon is going to be less attracted to other argon atoms than ammonia is attracted to other ammonia molecules. So we've done induced dipole. I didn't show it graphic, or I did not depict it here, but I'll do it right now. So we have also ion-ion. Remember that? We talked about this being the strongest force. So here's chlorine, 7 electrons if you look on the periodic table. Here's sodium. It has 1 electron if you look at the periodic table. So sodium, if I wanted to draw the Lewis structure for sodium chloride as a cation and chloride as a anion, I could draw it like this and just say, hey, look, you know, the electron's gone. So that would be chloride. Alternatively, I guess you could draw sodium having 0 valence electrons, or you could actually draw it as having a full set, like a full octet, because it has a lower set of orbitals that have been filled once you take that electron away. but I think this is probably less confusing just to draw it with nothing. So this is going to have a plus charge. This is going to have a minus charge. I'm not using deltas here. Why am I not using deltas? Is that a difference of 1 electron? Like we used to have the number of protons and electrons being equal. Now it's 1 less electron than protons for sodium, and it's 1 more electron than protons for chlorine. Is that a partial charge, or is that a full charge difference? Full charge difference, yes. These are all partial charge differences. So that's why we draw deltas here and we don't draw deltas there. And if you thought partial was not as good as full, you were correct. This is a much stronger force. That's why table salt, sodium chloride, is a solid and ammonia is not. Ammonia, if you get solid ammonia, not solid ammonia. If you get pure ammonia, that's the word I was looking for, pure. If you got pure ammonia, it's a low boiling liquid. So I think you put it in your hand, it might get a little bit to evaporate. And I think it's like bad for you, so don't actually put it in your hand. Yeah, it's a liquid and at room temperature, I think, or maybe a little bit below room temperature. And this stuff is not. This stuff is very, very solid. I'm kind of jumping ahead to myself a little bit. So let's depict some hydrogen bonding. So I covered everything. This is how you depict ion-ion bonding, right? You'd say, oh, look, there's an attractive force between these two because there's a positive charge and a negative charge. These things are very attracted to each other. Here you could draw a dipole-dipole because you have a partial negative charge and a partial positive charge. They're less attracted to each other. Okay, you know, that's fine. They're a little less attracted to each other than, actually significantly less attracted to each other than if you had a full charge difference. But same idea, right? It's still electrostatic interaction. It's still positive and negative charges attracting each other. Same force that brings magnets together is bringing these molecules together and having them want to be closer to each other. Guess what? Induced dipole. Induced dipole is basically a temporary version of this, right? So we're talking about different extremes of the same phenomenon. Charges, pluses and minuses going together. But we also know that there are these things that are bonds, that are shared electrons that are different, right? Like this hydrogen and this nitrogen are not attracted to each other in the same molecule because of a charge difference per se. It's because they share electrons. They have a bonding orbital that are being occupied by the same electrons. So it's a slightly different phenomenon. It's still based in electrostatics. It's still based on the electromagnetism force, one of the fundamental forces of nature. But it is not quite the same thing. It's not just a diluted version or a more powerful version of this ionic bonding. It's different. So hydrogen bonding is probably closer to this kind of bonding conceptually, but it's not as powerful. So don't think that things that are hydrogen bonded together are as tightly held together as things that are covalently bonded together. One hydrogen bond is usually not as strong as a covalent bond. But you can kind of think about it like that. So what do you need for a hydrogen bond? You need an X-type atom, a very electronegative atom. So X has to be nitrogen, oxygen, or fluorine. And you're going to need one of these that's bonded to a hydrogen, and you're going to have to need another one of these that is somehow has like a lone pair of electrons that is available for being a hydrogen bond acceptor. So let me draw this. Picture's worth 1,000 words. Let me draw it out using just copying this thing. So, here's ammonia. We did water, I think, or at least have a YouTube clip of water so you guys can see how to do the Lewis structure for water and know what the structure, the geometry looks like. I'm drawing it bent. See how I'm not drawing it like with hydrogens in a straight line, making a 180-degree angle, because this is not a 180-degree angle, not a linear molecule. It's bent. So there's a lone pair of electrons on this oxygen. This oxygen has a very, partial negative charge. You can't really say very when I'm sitting, like I have on the same screen this full negative charge. It's still partial, not full, but it has a partial negative charge, and these hydrogens have a partial positive charge. There's a lot of deficiency in like a lot of time, this hydrogen doesn't have electrons around it. Sometimes, like a lot of the time, the nitrogen's hogging electrons in that bond. And a lot of times, the hydrogen doesn't have those as much electrons surrounding it. It's not like it's an equal sharing, it's actually an unequal sharing. So you'd have a delta positive for this hydrogen, depicting that a lot of times this proton in the nucleus of hydrogen doesn't have a lot of electrons around it. And so you could actually have an interaction here where the electrons from the oxygen are involved in an interaction that's a lot like a covalent bond. In fact, in my mind, I think about it like a covalent bond, but you don't say that in exams because you'll get them wrong. So don't ever say that this is a covalent bond, but it seems to be a lot like a very weak covalent bond. So you can be schizophrenic about this until you pass your qualifying exams in graduate school, at which point you can be like me and be like, haha, I have my advanced degree and I know how things actually are, and it's a lot like a covalent bond. But you're stuck right now. So you're going to have to say, oh, it's not a covalent bond, but deep inside in your heart of hearts, you think of it as a covalent bond. It's temporary. I mean, if you have water in a solution floating around, these things get formed and broken all the time. The hydrogen bond requires that there's a lone pair on one of these three elements. That's what this oxygen is doing here. It's providing this lone pair. It also requires that there's a covalent bond between hydrogen and one of these elements again. So here's a nitrogen with a hydrogen that's bonded to it, and that's all you need. So these two molecules will actually probably be more attracted to each other than if they didn't have this interaction available. So if I had ammonia in water, I would expect ammonia to actually be very, very, very soluble in water, and I would expect it to be very stable as a solution in water and not likely to evaporate very quickly because it's constantly being engaged in these hydrogen bonds and being kind of stuck to a water. So another point I should bring up about these as you move on to other courses, in real life we have a lot of, you and I as chemists, or at least in this classroom as chemists, we get each other, right? Like we understand each other on a very basic level. Oh, sorry about the pun again. On a very fundamental level, right? And when I talk about chemistry, and I told you guys what the essence of chemistry is, not the book BS definition about the science of change. Chemistry is really about, the essence of it is about those valence electrons and what they're doing, right? Not the core electrons. That's for physicists with their lasers to excite. And it's not really about the nuclei so much. That's for like nuclear chemists or chemical engineers or physicists to create atom bombs and blow each other up with. That's totally different. We think more about what these valence electrons are doing, what the highest energy electrons are doing, or alternatively, what orbitals, spaces for electrons that are the lowest energy are available to be occupied. That's kind of what chemists think about all the time. That's what these Lewis structures are depicting, right? These are not all the electrons in the molecule. They're just the highest energy ones. They're the valence electrons, right? I didn't draw all the electrons for this oxygen. The 1s orbital electrons, they're not depicted here. This hydrogen bonding interaction, for some reason, I don't know why, people talk about it backwards. Okay, so if you're talking about it from a chemicals perspective, you'd say, okay, there's an interaction. Where are the electrons coming from? From the oxygen. So you'd call this the hydrogen bond donor. Not correct. For some reason, the terminology is that you look at the hydrogen as somehow being the coin of the realm, or the hydrogen is somehow the thing that's interacting, as opposed to being an electron-centric view. So you would call the ammonia molecule the quote-unquote hydrogen bond donor. And every time I hear somebody say this, it bothers me. And it should bother you too. So I'm trying to make my neuroses contagious here. So the correct way to actually talk about this, the way that everyone's agreed to talk about this, is that the ammonia is the hydrogen bond donor because it has the hydrogen that's involved in the interaction. And you would call the oxygen the hydrogen bond acceptor. Even though chemists would say, nah, not really. What's really going on here is that these electrons are interacting with this hydrogen. They're the smaller thing. They're the thing that's actually being donated, really. They're the thing that's doing the work. But We don't talk about those. We just think about, when we're naming these, we name the acceptor as being the thing that doesn't have the hydrogens, and the donor is the thing that does have the hydrogens involved in the hydrogen bond interaction. So you could have an F here that's connected to the hydrogen covalently, and it would still be a hydrogen bond. You could have an N or an O. You could have an F, an N, or an O here. Doesn't matter. It has to be of those elements, and it has to be a hydrogen that's bridging them, and there has to be a lone pair that's available to actually allow for that interaction. Okay? Good? I think people now, a lot of chemists are starting to say, well, we can characterize this interaction. We can start thinking about other things that are very unusual involved in hydrogen bonding, way outside the scope of the course. I'm trying to show you, like, your everyday on-the-street hydrogen bond interaction. This is what you're going to see. Okay, so think about it like this. These are the things you look for. Those are, you need to have these elements, at least one of them connected to a hydrogen covalently, and you need to have, again, one of these elements, could be a different one, doesn't matter, with a lone pair available for donating. Now, this is a stronger interaction than a dipole-dipole interaction, but it is not as strong as an ion-ion interaction. So I've shown you all the interactions, and we came up with a hierarchy for these that, at least on a one-off basis, that's strongest on this end, weakest on this end, right? So ion-ion is the strongest, next strongest hydrogen bonding, dipole-dipole is the third strongest, and London dispersion forces are the weakest of the four. And I've showed you how to figure it out. And the only one I really didn't show you how to figure out whether or not it's happening is London dispersion forces, because it's basically happening all the time. So if anybody asks you, hey, here's a molecule or an atom, is it involved with London dispersion forces? You would say, yeah. Just always, yeah. And it could be a molecule that's better for London dispersion forces. It could be a molecule that's weaker for it. But ultimately, every molecule is going to have nuclei and electrons. Every atom is going to have a nucleus and electrons. And those electrons might be on one side more than another. Now, you might start thinking about whether or not the shape of the molecule is more appropriate for London dispersion forces. If the shape of the molecule has more surface area, if it's more like a line, if it allows for more stacking, things get allowed to get closer together, then they can attract each other more. You can have closer, more powerful London dispersion forces versus molecules that are more shaped like balls. It's hard to get more alignment, more stacking if things are shaped like balls. You're not going to get a lot of like surface area on top of other surface area getting close. And that's kind of intuitive, but you can see shapes and we'll figure that out. Okay, so let's talk about how these phenomena manifest in real life. Like, I shouldn't say in real life, that's kind of, ethnocentric or macrocentric. How they manifest on huge scale, right? So we were talking about these all being attractive forces. So if there are more of them, or if there are stronger ones present, then you would expect that ions or molecules or atoms would be held closer together or be more cohesive towards each other, right? More attractive means more attracted. Good? Make sense? Too tired? Okay. These are all things that are very powerful. I would get mad at you, and I don't know if this is in the final, but it might not be. I don't think I was clever enough with any of the questions, but I should have put one in there. There are things called polymers. They're huge macromolecules. Disregard those for a second, okay? For these small molecules, for things that you could actually write out, for things that don't weigh kilograms each, for things that just weigh, 1 AMU or 1,000 AMU, things that you can draw on a piece of paper. These molecules, the force of gravity between them is really small. It's crazy small. It's not really enough to make them actually be very cohesive at all. What dominates on this scale at these low masses is electrostatic interactions. Positive charges and negative charges attracting, negative charges repelling other negative charges, positive charges repelling other positive charges. Do you guys remember how I was blowing your mind by saying that, hey, most of like a solid or a liquid is actually empty space, and then inside the molecule, actually most of it's empty space? Why does my hand not fall through this table?
Your hand is more dense.
Regardless of how dense it is, this is mostly empty space. Okay, so there is something called a neutron star. Have you guys ever heard about this? Neutron star? That's like a star that's like gone through some sort of solar evolution or stellar evolution, and it has burnt out all its fusion ability, and maybe there's some sort of like explosion or something that condenses it, but the nuclei in a neutron star are actually like, it's like one big nucleus. All the neutrons are like right on top of each other. Okay? I'll admit that's pretty dense. That's like super duper dense. All right? But for everything else that you and I deal with, like everything else physical, it's not like a black hole or neutron star, it's mostly empty space, no matter how dense it is. You have lead. That's still going to be mostly empty space. What's keeping my hand from going through this table is that there are electrons, outer electrons around molecules in my hand, and there are also electrons around, like the outermost electrons in molecules in this table, and they are both negatively charged, and they're both leptons. They both don't like pack into orbitals like as many as they want, so they are repulsive to each other. They can't be pressed into each other very much. It takes a lot of gravity, like a lot of gravity, like a huge star collapsing in on itself to get rid of that, to overcome that force. So that's why my hand doesn't go through this table. That's why fusion's very hard to do. So that's why we don't have like fusion, powering everything, at least not yet, because we don't have the ability to figure out how to do this ourselves. It takes a lot of energy to overcome a hydrogen atom getting really close to a hydrogen atom so that their nuclei touch, because the electrons are just so remarkably unattracted to each other at that close space. And if you actually even had protons, it would be a similar problem, because if you just had protons coming to each other, it'd be a positive charge and a positive charge having to be forced really close together. It's hard to do. So that's the source of like why we don't just like collapse into each other into like a giant, or not that big of a black hole, but into like just one black hole, because we are having these electrostatic interactions that don't even let our atoms get all that close together, or our molecules get all close together. Like that creates a atomic radius or a molecular size. That's the interaction that stops it. That's the interaction that dominates at the molecular size. It's electrostatics. It's not gravity, right? Gravity's not that great unless you have a lot of mass. So even things like the moon they're not massive enough to keep an atmosphere. Okay. So what I don't want you to tell me is that like, oh, this thing has a higher melting point than this other thing, or it has a higher boiling point than this other thing because it's more massive. Irrelevant at this scale. The mass is completely irrelevant at this scale. It's just too small of a mass to really have gravity mean anything. Okay. So intermolecular forces. If you have weaker intermolecular forces, then you're going to have lower boiling points, lower melting points, higher vapor pressure. Vapor pressure is the amount of pressure that a liquid has at the surface of the liquid that comes from molecules just kind of jumping off the surface of the liquid. All of these phenomena, lower boiling point, lower melting point, higher vapor pressure, I suppose I could actually have some solid properties too, like strength or toughness or something crazy like that. I'm not smart enough to do that. I'm not a material scientist. I guess I should ask somebody and have them generate stuff for me. But these are all manifestations of the same underlying phenomenon, that weaker intermolecular forces mean that the molecules are less attracted to each other and it takes less energy to move them apart. That's all. So it takes a lower temperature to boil off to have individual molecules just sort of leave the liquid. It takes a lower temperature to melt a solid if there are weaker intermolecular forces, because there's less things holding them together. There's less force holding them together. It takes less energy, less thermal energy to vibrate those molecules out of there. Right? Make sense? That's the idea here. Higher vapor pressure, same idea. You have the surface of a liquid. More of those molecules are going to be jumping off the surface of the liquid if there's less forces holding them to that liquid. If it's more attractive, to be in that liquid, then you'll have a lower vapor pressure. If there's more attractive forces between molecules, it'll take a higher temperature, more energy to actually melt it. And if there's a liquid with a lot of attractive forces between molecules, it will take more energy, a higher temperature, to actually boil off to get some of those molecules to leave the other molecules because they're very attracted to them. So this is how intermolecular forces manifest themselves in our daily lives. So something like water. I bet I have some good examples here, but come on. Oh, these are not bad pictures. We can go back to these if I have time. Okay, so let's ask this question. Which of these molecules would have hydrogen bonding in the liquid state? What am I looking for hydrogen bonding? What am I looking for? What are the prerequisites? There were 3 elements, right? N, O, and F. Yeah, nitrogen, oxygen, and fluorine. Do any of these things have nitrogen, oxygen, and fluorine? What's the atomic symbol for nitrogen? N. Do you see an N anywhere here? Okay. You can probably break down this work into things that are embarrassingly simple. Okay, I don't want you to think that there's any magic here. If it was really hard, I couldn't do it. So, especially not like off the cuff like this. So there's got to be a trick. You guys know I'm not that bright, so it's pretty easy. That's what nitrogen looks like. That's the Lewis structure of nitrogen. So for hydrogen bonding, you need there to be a lone pair on one of these 3 elements, allowing for, that would be like the hydrogen bond acceptor, and you need to have a hydrogen covalently bonded to one of these 3 elements again. That would make for the hydrogen bond donor part of the molecule. This has both, right? Ammonia, this is the Lewis structure for it. It has both. So I know none of the other ones are going to have hydrogen bonding because they don't have N, O, or F in them. So only C is the right answer. This one's going to have hydrogen bonding. C. Okay. Which of these would have a dipole-dipole attraction in the liquid state? So we'd have to actually think about which of these molecules has an overall dipole moment. For hydrogen, the Lewis structure is going to look like this. It's just going to be H bonded to H. What's the electronegativity difference between the different hydrogens? 0, right? Hydrogen will have the same electronegativity as hydrogen, so neither one's going to hog the electrons more than the other on average. So there's no permanent dipole here. That means that there's not going to be any dipole-dipole interaction. You need to have a permanent dipole in order to have a dipole-dipole interaction. So hydrogen is out. For ammonia, we did the Lewis structure. It looks like this, and there's an overall dipole moment. There's an overall dipole moment that looks like this, right? Where you have a dipole that points towards the negative end and points away from the positive end. And that overall dipole moment means that this thing's going to have a dipole-dipole interaction, right? How about methane? Each CH bond is not really polar at all. I would call it a nonpolar bond. So for that reason alone, this thing is going to not be polar. If you were to draw out the Lewis structure and then figure out what the geometry of it is, you would find that the geometry of it is tetrahedral. So even if, and it's not true, but even under the false assumption that each CH bond had a dipole moment, they would all cancel each other out because they are symmetrically arranged around the carbon. For hydrogen chloride, HCl, if I was to draw that out as a Lewis structure, it would look like this, HCl. Let me make that bond look more like a bond. There we go, HCl, boop, 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 boop. Which is more electronegative, chlorine or hydrogen? Chlorine is, and you could look it up too. So chlorine is more electronegative. That's going to have a partial negative charge. Whoops. Partial positive charge in hydrogen. So this is going to have a dipole moment. And the dipole moment is going to look like this. Points to the negative end, points away from the positive end. So this could have permanent, it does have a permanent dipole, so it could have dipole-dipole interactions. So both HCl and ammonia have dipole-dipole interactions. Okay, how many of these molecules would experience London dispersion forces? For every one of these, if I asked you, you should answer they all could have them, so all of them have London dispersion forces possible, so the answer is all 4 of them could. Pretty easy. It's always the answer that they could have some, so therefore they all have a little bit of induced dipole, induced dipole, or van der Waals, or London, or dispersion, or London dispersion forces. I mean, there's like lots of names for it. Okay, so we talked about vapor pressure. Like I said, it's how much the molecules jump off of the liquid surface. It creates a pressure if they're like bouncing into the surface of the gas. And like I said, the less attraction there is, the more vapor pressure there's going to be. So molecules that really attract each other a lot are going to be more in the liquid phase. It's going to take a lot more energy to actually move them out. And when they're in equilibrium, very few of them will actually be jumping out if there's more intermolecular forces, if there's stronger intermolecular forces. Okay, so I want to end this topic kind of with the whole going to like macro things that you and I know, and thinking about how these intermolecular forces actually contribute to them. So here is the Lewis structure, or actually the geometry. I'll just go straight to the geometry to cut to the chase. Here's the geometry for methane. Tetrahedral, so I have to draw like one of these bonds going into the plane and one coming out of the plane with a wedge. So there you go. Symmetrical molecule, tetrahedral. And here's water. They have about the same mass. So the atomic mass of both of these is about the same. Guess what? Sorry, terrible Lewis structure. I got like the wrong number of electrons. Okay, so here's the scoop. If we think about these, which one is going to have the higher boiling point? Water or methane? Water will have the higher boiling point. At room temperature, methane is a gas. I don't even know what the boiling point of methane is. It's going to be some sub-zero temperature. I don't know. Water, the boiling point is 100 degrees Celsius. Why is its boiling point higher? This boiling point is higher because it can engage in hydrogen bonding with other water molecules. So that makes it much higher boiling point. How does it involve in hydrogen bonding? Well, a hydrogen from another water molecule, like, let me just draw, blop, blop. There we go. So a hydrogen from another water molecule can interact with this water molecule. It could act as a hydrogen bond donor. Let me draw the full Lewis structure so I don't freak anybody out. There we go. So this hydrogen would act as a donor. These electrons, and this oxygen would act as an acceptor, a hydrogen bond acceptor. And this would be a hydrogen bonding interaction. Okay, so what? I mean, that's kind of neat, but let's go a little bit more interesting. So there are there's one more intermolecular force that water participates in. It has a dipole moment, right? Everybody, yes, it has a dipole moment. Which end is the partial negative charge? Is it the hydrogen end or the oxygen end? Right. The oxygen has a higher electronegativity. The hydrogen has a less electronegativity, so this is a very polar bond. It's polar covalent. So the oxygen in each of these bonds will hog more electrons. So each of these bonds have a dipole moment that looks like this. There'd be like a partial negative charge here. Sorry, positive charge on the hydrogen. Whoops. Partial negative charge on the oxygen. And the overall dipole moment, if I was to add these together, would look like this. So the hydrogen end of the molecule has a partial positive charge, and the oxygen has a partial negative charge. So this water molecule not only engages in hydrogen bonding, but it also engages in, what do you call it? Dipole-Dipole interactions. So let me engineer a molecule, it's not that hard, to be similar to this, but that has no ability to do hydrogen bonding. So this is dimethyl ether. Whoops. Eventually I'll get this right. There we go. CH3. Dimethyl ether. So let's go through these. We got London dispersion forces. I guess I'll just type them out because I'm going to get confusing. So London. Sure. Let's call them London. And then we got hydrogen bonding. Wait, hold up. Let's do all of them, right? So we got London dispersion forces. We got the next highest one is dipole-dipole. Yeah, that's right, dipole-dipole. And then the next one is hydrogen bonding, right? And the next highest is ion-ion. I know, I just changed the ordering. Yeah, so I'm not trying to say that these are, the ordering is arbitrary. I'm not trying to say that the power of them or the strength of them is arbitrary, but this is like the weakest, and this is the strongest. Okay. So I don't need pluses here. It's not like I'm doing a reaction. So here we go. We got those, and here's one I know for sure. So NaCl. Okay. So London dispersion forces. Does methane have London dispersion forces? Does blank have London dispersion forces? Yes. Okay. So all of these have London dispersion forces. Yeah, they all do. Dipole-dipole. Does methane have dipole-dipole interactions? Yes, no. Who votes yes? Who votes no? All right, the no's are right. So there's no permanent dipole in methane. Dimethyl ether. Does this have a permanent dipole? Yes or no? Who says yes? You got one person, two people for yes. Who says no? We got three people for yes. You were all right. I didn't count your hand until very end, but yeah, got it. Okay. Dipole-dipole. Does water have dipole-dipole? Who votes yes on this one? All right, for the rest of you, you guys should be getting the pattern recognition going on. I got like 5 on this one. I should have like all of you going yes, because this is exactly the same instead of hydrogens. This one has methyl, and this one has methyl instead of hydrogens. Same idea. So all of these two so far have dipole-dipole, and I would say no on this one. So these are charge separation. A dipole needs to have, that's a bad use of words, isn't it? So this is a full charge difference between the sodium plus and the chloride minus in sodium chloride. It's not like there's one side of the sodium that has a permanent dipole, an extra positive charge, and the other side of the sodium has a permanent negative charge. The permanent charge comes from there being a separation of those two ions. So technically there's no dipole-dipole in this. Hydrogen bonding. Is there any hydrogen bonding in methane? Yes or no? Who says no? Who says yes? There's not going to be hydrogen bonding because you need to have nitrogen, oxygen, and fluorine. One of those two, or one of those three, or multiple of those three. You need to have a hydrogen bonded directly to one of those elements, and you also need to have a lone pair available on one of those elements as well. So hydrogen bonding, no. How about for dimethyl ether? Who says this has hydrogen bonding? Okay, we got like 4 people. Who says it does not have hydrogen bonding? 1 person. Dimethyl ether does not have hydrogen bonding. If I have pure dimethyl ether, so just a sea of this stuff, yes, it has hydrogen bond acceptors, these lone pairs, but there are no hydrogen bond donors. There are no OH bonds to act as hydrogen bond donors. So this would have no hydrogen bonding if it's a pure solution of just this stuff, or a pure like gas tank of just this stuff. So no. Hydrogen bonding in water. Does water have hydrogen bonding? Who says yes? All right, good, yes. Overwhelmingly yes. NaCl, does this have hydrogen bonding? No. Excellent. No. Okay, and then ion-ion. Is there an ion here? Is there like a permanent full positive charge on any of these elements? No. How about on dimethyl ether? Yes, no? Okay. How about on water? No again, right? And then for sodium chloride, is there a charge separation? Yes, this is ionic bonding, it's ion-ion attraction. Okay, great. So check mark. All right, so let's just go through these and think about what's going on here. So table salt, NaCl, that's a solid at room temperature. I've never seen molten table salt, and I hope I never do. So I don't know what the melting point is, but it's a really high temperature. It takes a lot of energy to break this apart. So as a solid, it's just as a pure substance, it is a very, very, very attracted to each other lattice, crystal lattice. It takes a lot of energy to break it apart. So this is of these different substances, this has the most intermolecular forces or inter-ion forces. So ion-ion trumps the other ones. It's not because this weighs more. It's because there's more stronger intermolecular forces based on electromagnetism, positive and minus charges attracting each other. How about hydrogen bonding? So the only substance here that has hydrogen bonding is water. And at room temperature, this is the only substance, I'm not sure about dimethyl ether. I'm not sure if this is a liquid. It might be. So it either has a boiling point that's very low, or it has a boiling point that's like, I think I can either get this at like freezing temperatures or at room temperature. So I can get this as a liquid at reasonably low temperatures on Earth. I can't, water's like present all over the place as a liquid. So this has a much higher boiling point than dimethyl ether. It also has a much higher melting point. So I see ice of water around all the time. I think I need to do really low temperatures to get this thing to be a solid. So there's much stronger intermolecular forces in water than there is in dimethyl ether because of this hydrogen bonding. I might be able to get a can of this, but if I leave the can open, it's going to evaporate pretty quickly. If I open up a bottle of water, it's going to evaporate much more slowly over a matter of days versus this being a matter of minutes or hours. Dimethyl ether, though, if I have a low temperature can, I can't actually work with it as a liquid. It's not a gas. Methane is a gas. Its boiling point is much lower than temperatures you find on Earth, than the boiling point of dimethyl ether. So the weakness of the intermolecular forces are manifested in the melting points and the boiling points, and you would expect going this way from ions, from compounds and molecules that have weaker intermolecular forces to ones that have stronger ones, that you end up having higher boiling points, higher melting points, lower vapor pressure. In fact, I don't even know if that's relevant in terms in sodium chloride, because it's a solid. And I mean, we can start thinking about macro physical properties.